This is Syed Bilal, and today I am going to explain you about RAID, that is redundant array of independent disk. RAID, that is redundant array of independent disk. Earlier it was known as redundant array of inexpensive disk, just because in the earlier times there were the hard disks which were very large in size, so their cost was also much, so we used to have some smaller hard drives just to reduce the cost. And now this RAID, that is redundant array of independent disk, we use it as a technique in which we use certain small hard drives instead of using a single one, just to increase the performance. The uses of RAID are: it is used to increase the performance, in fault tolerance, and in reliability. Okay, so RAID can be classified into different types like RAID 0, 1, 2, 3, 4, and we are going to see each and every one. So RAID 0. In RAID 0, as you can see in this figure, we divide the data into strips, and these strips are divided among the number of disks present. So in this case, the entire data is divided into strips, and these strips will also be divided among the disk 1 and the disk drive 2. As you can see, I have given one example. If you ask one man to write from A to Z, he will take approximately more time than if you ask two men to write from A to Z. That is, ask one man to write from A to M and ask second man to write from N to Z. The time taken by them will be less as compared to a single man. So similarly, if we use two disks instead of one, then it will help us to increase the performance of a system. In RAID 1, what we do is we create the copy of the entire disk into another disk, as you can see in this figure. The disk drive 1 and the disk drive 2 is just a copy of disk drive 1, and this process is also known as mirroring. It just helps to increase the reliability, because if one of our disk get lost, then we have another disk for the same access of data. This RAID 1 will not increase the performance of the system, and therefore it is very expensive. Now, RAID 2. RAID 2. In RAID 2, we use error correcting code like Hamming code. We split the data into number of disks present, while the rest of the data while rest disks are used for storing the error correcting code. Here, more than two disks are used for error correcting code. This may help in faster reading, but for every write operation, we have to calculate the error correcting code. So, it is the slower process. As the write operation also requires minimum 3 dedicated disk drive for storing the error correcting code, as more than 2 bits are used for storing the error correcting code, and it is also the expensive, so it is not used much. RAID 3. In RAID 3, we overcome the RAID 2 flaws. In RAID 2, we use minimum 3 number of disks for storing the error correcting code. But here we use the concept of parity. That is, except the error correcting code, we maintain only a single disk for storing the parity values, while among the rest of the disk, the data is divided bitwise. Parity values is XOR of A1, A2 and A3. If they contain even number of ones, the parity value is set to 0, and if the odd number of ones, then the parity value is set to 1. This helps in increasing the data transfer rate as well as the disk participate in every read and write operation, so performance will be higher. Uh, like earlier, we have discussed the example that two men can write from A to Z faster instead of just one man. But in this case, If all the disks are participating in every read and write operation, then the number of accesses increase as the number of disks are free to service the new read request. In RAID 4, RAID 4 is similar to RAID 3. Only the difference between the RAID 3 and 4 is in RAID 3 we divide the data bitwise, but in RAID 4 we divide the data blockwise. As the blocks are bigger than the disk, so far as a small read or write operation, only the disk will be used. So rest of the disk will be available for service only our read and write request. This rate increases the number of simultaneous access, but its data transfer is less as compared to RAID 3. Okay, because all the disks don't participate in every read and write operation, RAID 4 is suitable mainly for large read and write operation. But if the content to be read and write is more than one block, then disk will also be used and the performance will be boosted. RAID 5. As we know, in RAID 3 and 4 we store the parity information in a single disk, and if that single disk is lost, then we will lose all our backups. So to overcome this drawback in RAID 5, parity data is divided evenly among the number of disks. Rather than maintaining the dedicated disk, any formula can be used for placing the parity values evenly. We store the parity values of our entire block in one disk, and the actual data of the block is divided into the remaining disk. RAID 5 reduces the potential overview of a single parity disk as one of our parity is used. It helps to reduce only one disk fail, but if two or more than two disks fail, then the RAID 5 won't help to restore the damaged data and all the data will be lost. In RAID 6, RAID 6 is similar to RAID 5, but in RAID 5 we store only one parity bit, so we could recover failure of one disk. But in RAID 6 we use B instead of 1. It's 2. We use 2 instead of 1. Extra bit stores extra data information to guide against multiple disk values. Error correcting code like read Solomon code are also used. It's 2 instead of 1. RAID 10. RAID 10 is the hybrid of RAID 0 and RAID 1. It has two types, that is RAID 0 1, RAID 1 to 0. In RAID 0 to 1, we first mirror the data and then is stripped between the copies of data. In RAID 1 to 0, we stripe the data and then mirror the data to form another copy of it. Thank you guys. That's all.